Hi, I'm Barnaby, and this is the StrathSEDS Critical Design Review for the Mach-24 launch competition. I'll hand you straight over to Jamie to go over an overview of our launch vehicle.
The launch vehicle will be single stage and dual deployment. There will be two ejections with either pyrodex or black powder. The fins will be through the wall, and the ejections will be controlled with an Easy Mini and Egg Timer Quark COTS avionics for redundancy. The changes since the PDR, the main ones are that the tubes are significantly lighter than we were expecting. The airframe has been marginally lengthened to accommodate the new design of the CANSAT and estimated volumes for the packed chutes. For the PDR, the CANSAT was an extremely basic design, but it's been much more fleshed out since. The fins have changed shape based on feedback we also received. They're no longer so swept back, and the configuration of the foretube has been marginally changed as well. The rocket will be split into four main sections: the nose cone and the main chute bay. At the front, the avionics bay with all of our electronics, the payload and drogue bay where the CANSAT and drogue chute will be, and the motor zone where all of the boat tail, the fins, and the motor will be housed. The nose cone will be a tangent ogive made of hand laid up fiberglass. It will be attached to the foretube, and the foretube and nose cone will separate as one from the coupler tube where the AV bay is located. The fins, based on feedback received from PDR, the fins are now much less swept back. This will help with durability on impact and significantly reduce their weight. Here you can see a direct comparison between the two fin designs. The fins will be made from water jet cut 3mm fiberglass sheet secured with a through-the-wall tab, which is 10mm long, and a chamfered leading edge to reduce drag. Our boat tail will also be the securing mechanism for our motor. The boat tail will be mainly 3D printed, and the closure for the motor will be secured into the boat tail, and the whole boat tail and closure will be screwed into the motor casing. This, once attached to the motor casing and motor mounting tube, will be once secured into the airframe directly as well as a sort of security measure. The motor mount tube will be a phenolic tube. It could be reinforced with fiberglass layup if there are any worries about the strength. The mount is also slightly smaller than the motor itself, but we've done some research which suggests this should be okay. If necessary, we could also fit a slightly longer tube in. The airframe itself, learning from last year, the avionics will be in a coupler tube, which will be much more easy to access. The coupler tube will be made of phenolic tubing, and the main airframe will be made of fiberglass. The tolerances between the coupler tube and the main airframe are quite tight, so this will need to be sanded out just to make sure that it will be consistently fitting well. The fiberglass tubes are notably lighter than what we were expecting and what the density for fiberglass in open rocket. However, we believe they will be adequate, but we will verify this through extra thorough testing just in case. Bulkheads and centering rings will be cut from the same glass reinforced plastic sheet as the fins. This will help us reduce costs. The recovery systems, to avoid having to reach so far into the foretube as well, the shock cord will be semi-permanently attached to the bulkhead in the top of the nose cone, and then that will be attached to the main chute and the rest of the shock cord from there. The rest of the attachment points can be seen in the diagram above with the black lines. We chose the 3mm GFRP sheet for the fins, bulkhead, and centering rings as we believe it's a good balance between the weight and the strength. And also using the same sheet for all of those means that we can reduce costs by just buying one sheet. On this side, we can see a table of the masses of the key components of the vehicle, as well as where the center of mass is located. In the rightmost column, you can see where, if we've been able to directly measure the mass of these components because we already have them, or if we've been able to sort of deduce masses based off known densities. Here you can see the graphs of our stability versus time and our center of pressures versus Mach number. As you can see, the stability margin gets a little uncomfortably high early on in the flight. We hope to reduce this or rectify this problem as soon as we can. For our motor, we'll be using a Pro 54 6-grain motor, which we have already ordered from Rockins and Things. On the outside of our avionics bay, there are some camera shrouds to reduce the impact of the mirrors we need to use to view the outside of the vehicle. We have done some CFD analysis on these shrouds to see the impact they'll have on the aerodynamics of the vehicle and the static margin. Some preliminary analysis has given some numbers for drag coefficients, and we'll do some more comprehensive analysis to check how that will affect the vehicle throughout the whole flight. For recovery subsystems, the drogue chute and CANSAT will deploy at apogee, and the main preliminarily we've got at 500 meters. To ensure we don't use too much powder, we'll be using we'll practically determine the amount of powder we should use. We'll do this ejection tests at fairly Moore. We'll start with 1 gram, as that's half the motor's ejection charge, and we'll work up from there. Using RocketPi and drag coefficients obtained from RAS Aero 2, we were able to get the drift simulations for our rockets. Using a westerly wind and a westerly point and rail, we obtained these values. However, it would work the same for any direction of wind, and we made the landing location easier to find. In the table, green is for any locations within 500 meters of the launch pad. Yellow's for less than 1,000 but more than 500, and red's for anything over 1,000 meters from the launch pad. This is based on a constant wind, but for our final simulations we use a weather forecast. For our shock cord, we've got 5/8 inch tubular nylon, which is 3.5 meter sections. We'll use Nomex to protect it, make sure that it doesn't get damaged in the ejection events. It will be connected to the bulkheads using M6 U-bolts and quick links, and the CANSAT will use a 16th inch Kevlar cord.
Moving on to the avionics we've included in the launch vehicle. So we have our ArduCam, the global shutter camera, looking through a mirror at the fins. That is going to an Octo 4C Plus with a radio expansion for telemetry. And then we have a Firefly 1.1 that is connected to pyro test LEDs, so that will allow us to see when it has fired a pyro channel to ensure it's close to the COTS computers without dealing with the E-matches. And then for our deployment, we have a Egg Timer Quasar and Easy Mini in a redundant configuration. So our telemetry link looks like this. We have two links, a backup link for the CANSAT with a completely separate system with a backup telemetry receiver on 868 MHz going into a secondary laptop. And then our primary link for the avionics and for the primary CANSAT will look like this, with a 2.4 GHz link and an 869 MHz link. So our position will be relayed from our Firefly 1.1 in the avionics through that 869 MHz link. That will allow us to point our tracking ground station towards the vehicle to align our high-speed link. Then our video stream will be received and decoded through the Raspberry Pi, sent over the laptop, and all of this will be streamed on our Twitch channel. So our real-time telemetry display will be using the StrathSEDS SpaceLink app, which will be available in the App Store, and we'll have a dashboard running on Twitch TV showing our live video stream. This is a previous example that we've had at a previous Mac. So the radio channels will look as follows, with an 869 MHz link at 160 milliwatts transmit power, which is well under our 500 milliwatts max allowed, and this is on 869 MHz, which has airborne use permitted. We will also have our backup telemetry channel at a slightly lower power, 25 milliwatts, on 868 MHz for the CANSAT. Again, airborne use permitted. And finally, a video stream channel with a 2.4 GHz at 100 milliwatts, which also, again, airborne use permitted. And our radio channels look like this. We are having two different things on 869 MHz. So our launch vehicle in the Firefly in the avionics bay, and the CANsats are on the same frequency using time division multiplexing, basically just taking turns transmitting so we don't talk over each other. Because we need much more precise position information on the launch vehicle, we will have slightly more, 70% of the time, dedicated to that, and 30% to the CANsat. Our backup is on a completely different frequency, 868, so we'll have a 100% transmit time, and same with the video stream, 2.4 gigahertz, will also have a 100% transmit time. So you can see in the middle here, the two whip antennas. Those are the examples of what are going to be going on the Fireflies in the rockets, and also on the Octo. You can see in the bottom left and top right an example of how our tracking ground station is looking. Slightly incomplete, as you can see in the bottom right, that's the Wi-Fi antenna. It isn't quite the 2.4 gigahertz antenna, sorry, which isn't on the model as of yet.
Now for a quick overview of our payload. Our CANsat will be assembled from a threaded rod, bulkhead and shell structure using M5 threaded rods to keep the CANsat together. There'll be 3mm glass reinforced plastic bulkheads on either side of the CANsat, and a 3D printed shell using recycled plastic to encapsulate all the internals. In these diagrams here, you can see the dimensions of the CANsat. The payload will be ejected at the same time as the drogue chute at the apogee of the flight. Additionally, at the same time as the vehicle descent calculations, we also simulated the descent of the CANsat. This was using the same method of using Rocket Pi, with simulated flights from 0 to 20 meters per second and 0 to 20 degrees from the vertical. As we can see, there's a nice diagonal line, so however fast the wind goes, we can land the CANsat in the correct range. The CANsat will have a 15-inch diameter parachute and is estimated to land at 14.3 meters per second.
So moving on to the electronic side of the payload, this is the sonic chamber, where we have a panel mount buzzer on one side, a microphone to record the input signal, and then the far end, another microphone to record our output signal. We will get the difference between these, and that should give us a measurement of the speed of sound. So the electronics in here, we've got a Firefly 1.1 that's providing our primary telemetry. And on top of that, we've got our sound processing expansion, where it will be connected to both microphones, do some processing on the data, and pass on that processed data onto our Firefly 1.1. Finally, we have a Firefly Mini providing our backup telemetry. That is the small, tiny board on the top right image. So on to the batteries. In the avionics and CANsat, we are using RS Pro 18650s. Those are used either in a 1S or a 2S configuration. Either way, the capacity is the same. So that is a 3.7 volt lithium-ion battery with a capacity of 2.6 amp hours. We also, for our Octo Rock, have a 10,000 milliamp hour power bank that's supplying 15 watts, so 5 volts, 3 amps maximum to the Octo. And that has, as I said, a LiPo battery and 3 amps continuous current. On the ground station, we just have a 12 volt lead acid battery that can do a continuous of 10 amps for over an hour, an instantaneous of over 90 amps for 5 seconds, with a capacity of 6.5 amp hours. Way, way more than we need, so should give us plenty of on-time for our tracking ground station. So on to the control for the batteries. So each computer, the Eggtimer Quark, Easy Mini, Firefly 1.1, will have their own individual screw switch for turning on. And Firefly 1.1 will have an additional remove before flight tag that you can see in that bottom right image for arming the pyro channels. Now moving on to the power budget, lots and lots of items here for the Firefly 1.1 power budgets. So this can be summarized in these two images. Basically, our main losses are to the radio and the MCU and the GPS. And in recovery mode, most of that will be going additionally to the buzzer. So you can see that our worst case average power will be about 600 milliwatts. Moving on to the CANsat, so this is just the expansion board, as for the 1.1 on its own will be the exact same. You can see that again we're not getting not as many components, but not that much current draw. So you can see that our worst case here is under 100 milliwatts, 66 milliwatts, so not too much. And most of that is from the processor. The power budget for Firefly Mini looks like this. Most of the components are very similar to 1.1, so not too different here, with our worst case power coming up at about 450 or 470 milliwatts. So, with those in mind, this is our time calculations. We are looking at a time of over 10 hours easily for every computer apart from the Octo. Now, the Octo, because it's so power hungry, can pull up to 15 watts continuously. So at that, with the camera pulling its maximum value, we're looking at 2 hours bare minimum. We will look into reducing the power use when we're on the pad and making sure we can arm that just before launch to really maximize our on time. So, because we have so many computers in our avionics bay, we've taken the decision to consolidate some of the power. So the Eggtimer Quark and the Firefly 1.1 both require a 2S lithium-ion battery. So instead of including 4, we've decided to get that down to 2, so they share a supply. That will be done using a distribution board with a diode to prevent any backflow issues. And you can see on the graph there, the Easy Mini will get its own battery, and that's looking at about 50 hours of its average runtime current. And the Eggtimer Quark, again, if it was on its own, would get over 50 hours, well over what we need. And if you look at the other two, avionics and Quark in flight mode, would still get over 10 hours with that. So that's a 1.1 on the Quark on the same battery. So well over what we need, and we still have additional redundancy as the Easy Mini has its own power source, so it shouldn't cause any issues.
And now for the testing section of the presentation. Here you can see the testing tables for airframe, the ejection tests, recovery testing, avionics testing, the mechanical side of the avionics testing, and the payload testing. We will give you all of these tables with the presentation, so you can look over them in more detail. I'm sure hearing me talk through all of them won't be particularly interesting.
Moving on to the testing for the electronics. We're going to start off with the COTS computers. Not too many tests here. These are flight-proving computers. We use them both in our IRW launch. So we're going to just do the basic test, just make sure they can deploy an eMatch, detect apogee in a simulated environment, so just a small tub that we're going to lower the pressure in, add it back on, make sure that they're deploying at roughly the same time. And finally, that they are detecting continuity as we expect. Now, our SRAD computers, Firefly 1.1 and Firefly Mini, have broadly the same components, so much of these tests are going to be common between the both of them. However, there is a lot of things here, so I'm not really going to go into that much detail. Just note that the main things there are making sure things can talk to each other, things are reading as they should, and they're accurate enough for our purposes. For Firefly Mini, we've done much of our initial test, make sure things can communicate, and Firefly 1.1 is still also in the initial stages. So moving on to the altimeters expansion, so that our speed of sound measurement. This is the second board that we are still in the end stage of designing. Again, this is just making sure all the chips can communicate with the MCU. We're resilient against noise in our measurements and noise in the environment, actual acoustic noise. Finally, there's also the ground station. So this also, a lot of tests we're going to be doing here. Tracking in static and dynamic testing using just a laser pointer. Long range tests on our low speed and our high speed links. Just to make sure we can get the kind of throughput that we need. So our range tests will probably be using the Clydebank Titan to Erskine Bridge, which is a 4.1 kilometer distance. We've used this in the past, and it's got pretty good line of sight, and it has about 103 decibel path loss.
Okay, so now we'll be moving on to the budgeting part of this CDR, and we thank all of our gracious sponsors for their help this year. We have the University of Strathclyde Alumni Fund, who were kind enough to give us £2,660 at the start of the year. We also applied for sponsorship from RS, And we were successful in that sponsorship application, and they gave us £300, which you could spend on their online store. JLC PCB gave us $205 worth of vouchers for their store, and we also got licenses from Altium, Ansys, and SolidWorks. Recall were also kind enough to cover our motor costs. However, this is a little up in the air right now, and we're budgeting just in case we can't go through them. So that cost for the motor will be around £458, and if we weren't able to achieve this through Recall, we have plans in place to go through the mechanical budget instead. So here is a breakdown of our miscellaneous budgeting. The main expense, of course, is the entry fee to the competition, and that's about £650. On top of that, we have the transport costs, which are £150, and that's counting towards petrol for getting towards and back from the launch site. We have our BMFA registration fee and some more launch costs as well. In terms of our lab costs, there aren't any because we have technicians who have agreed to water jet cut the fiberglass sheets for us in the lab, meaning there are no costs for this. There are also no costs for testing, and accommodation will be covered by our members. The ground station itself, we're looking at around £140 for the tripod that we plan on using. But of course, if we can't afford this, then we have plans in place to use the existing tripod already that we used in previous years. So here are the components that we've budgeted for. This is split mainly into the mechanical and electrical teams. So the convention here is that everything in black we have bought, everything in red we have to buy. So you can see there for the mechanical team, we've covered our motor, our stickers, our airframe, our payload bay, and our rail guides. And we still have to buy the epoxy, some hardware, some tools, and of course the tripod and a few other components that are listed. The electrical team have bought their radios, cameras, PCBs, which are the Firefly computers, and we also put in the RS component order that's also listed on the slide. And they still have to buy some power banks and some expansion PCBs as well.
Here we can see the timeline remaining between now and the launch event in July. I'll send you a more detailed image of this so you can look in a bit more detail than this. So to wrap things up, in terms of major accomplishments since the preliminary design review, our CANSAT design has been greatly improved since then. We've really started to flesh out the interior, and the design of the launch vehicle as a whole has greatly matured since the preliminary design review. It's really starting to come together. Finally, some of our components have started to arrive, as well as our flight computers, Firefly 1.1 and Firefly Mini. They're both also starting to get tested. Honestly, it's really cool seeing them boot up for the first time. However, in terms of unfinished work, as you probably saw earlier in the presentation, we've got a very high static margin. This could be fixed by either reducing the fin size or by ballasting either the aft or the fore of the rocket as appropriate. We're looking to commence construction of the vehicle at the end of our exam period that ends about the end of May. So far, we haven't got any of the vehicle constructed. On the electrical side, our payload expansion boards are not quite finished in the design process. They'll look like they'll be finished in the coming days, and we'll have an order put in at the beginning of next week. And finally, our tracking ground station hasn't really been touched since before the preliminary design review. That's something we're going to look into a lot, especially as our people who are dedicated to our tracking ground station finish their exams fairly early in the period. Just to wrap things up then, I'd like to extend a lot of thank yous to our sponsors who are helping make a lot of this possible for us, as well as the Strathclyde Alumni Fund and the Strath Union. And finally, I'd like to extend a thank you to the whole team. It's been a huge undertaking for everyone, and I'd like them to know that I greatly appreciate it. Thank you for listening.